Okay, the next topic is conservative and non-conservative forces. All right. Now, whenever we calculate the work done, right? The work done is force into distance, displacement. Fine. So, right, whenever we try to calculate the work done, right, we use the forces, and if the work done is independent of which path it has been taken, in the sense there is a force applied and what path the object has taken to reach a point. For example, let us consider this is a point A and this is a point B. Now, because of the force applied, object can move from A to B like this. Possible, right? And also the object might move in a different path and still reach B. Object may take a completely different path like this and it may come and reach B. All right, you can see that there are multiple paths possible irrespective of the path the object takes to reach B if the work done remains constant, right? Whether you go from straight path, whether you go from a path which is right away from the which is far away or which is a different path, right? Irrespective of the path, if the total work done remains constant, the same, then that is called as a conservative force, right? Look at the example, right? Let's go back to one of the example we solved yesterday. Okay. Work done. Yeah. So this problem. In this particular problem, the object moves from A to B, B to C. Right? There is a fixed amount of force that is minus 2i plus 6j plus 8k. Now we saw that if it moves from A to B and B to C, the total work done is minus 28 plus 60. So that gives you 32. Also, if without moving to B, if the object directly moves from AC along the path AC, then the work done is 32. You see, it is independent of the path in which it travels, right? So something like this, you had a point A, this is a point B, this is the point C. So A to B, you spend minus 28 joules. B to C, you spend 60 joules. So if you move directly from A to C, you spend 32 joules, which is same as minus 28 plus 60, right? So you see that this kind of forces are considered as the conservative force, right? Okay, if the work done in the presence of a force is independent of the path of displacement, then such forces are called conservative. Conservative forces. So object moves from A to B irrespective of which path it is, right? Maybe I'll call this is 1, this is path number 2, this is path number 3. In such case, the W1 work done along path 1 is equal to W2 is equal to W3. All right. But for a conservative field, now you see it is independent of the path taken. So the fundamental idea of the conservative nature of the force is that this indicates that if I start from a point and I travel around some path and I come back to the same point, right? You started from a point, you moved around a path and you come back. Now, can you guess what is the work done? This work done becomes equal to zero now because you start from a point, you move to the same point, displacement is zero. You might have traveled through a path, right? So, but you see, since the displacement is zero, work done becomes equal to zero, right? So, because of this, for a conservative force, if you have a conservative force system for a system, the, the work done in a closed path. So I start from a point A, I come back to the same point A, irrespective of what is the path for the traversal, right? Work done along a closed path. In a closed path is always equal to zero because no displacement. All right. Now we have another type coming up. So that is the second type, non-conservative force system. So let's try to give a definition over here. If the work done is path dependent, right? Then the force is said to be non-conservative force. So in this case, right, it is not independent of path. It is dependent on path. In the sense, I move from A to B, right? You have three different paths. This is path one, maybe another path. This is path number two, and a third path. That is path number three. So here W1 is not equal to W2. That is definitely not equal to W3. So because of this point, right, we will be able to write that along a closed path, the work done is not going to be zero, right? Anyway, it may look it may not be so very clear when I say that the displacement is zero. Still, you have done some work because the direct application to the equation says that okay, displacement is zero, so you have what you call as the product becoming equal to zero. It looks like that, but anyway, we'll justify this later. Okay, so here in this case, for a non-conservative force system, the work done along a closed or in a closed path is not equal to zero. Okay, we need a little bit of more mathematics to prove that, right? As of now, we'll skip that. Okay, let's move further. Now, let us try to give a very clear-cut comparison about the two types of forces. conservative and non-conservative force. So in case of a conservative, okay, let's do the comparison. So on this side we'll write the conservative force system. On the other side we'll write the non-conservative force system. Okay, the first point is very clear now. We already know about this, right? The work is path independent. Here, the work is path independent. So work on a closed path equal to 0. Here, the work is not equal to 0. Right. The other difference is, we'll prove this later. So the word called potential energy. When we say potential energy, we'll define the energy later. But the potential energy is defined. There is a valid answer for conservative force. Whenever the force system is conservative, you can calculate the potential energy related to those forces. Okay, so I'll write the word called potential energy is well defined for conservative force, right? But if the force system is non-conservative, the potential energy is not defined. If the system is non-conservative, we cannot calculate the potential energy. Okay, that's the point. Then we go for another point in the conservation, right? Let us try to write the examples. The gravitational force system, the electrostatic force system, the spring forces, etc., fall under the conservative force system. Whereas the example for non-conservative force is the friction. Then we have what is called as a the viscous etc. So they are called as the non-conservative forces. All right. Then we'll move ahead. The next topic is the kinetic energy, denoted by G. Right. So the capacity of a body to do the work because of its motion, right, is called as the kinetic energy. Right. This is the ability or capacity of a body to do the work because of its motion is called as a kinetic energy. Now, so whenever we say the body is possessing motion, body is under the movement, there will be a velocity associated with that. Acceleration may be there, may not be. Okay, but velocity will be there. So we try to define the kinetic energy of a body under motion by using its mass and the velocity, right? So what is the equation to calculate that? So kinetic energy is equal to half into m into v square. So here the m is the mass of the body. Since it is under motion, there will be a velocity associated with that. So numerical value of the kinetic energy, half into mass into the velocity square. Right. Now, so the work it has to be calculated. So basically, this is the work, right? It's a ability to do the work by virtue of its motion. So we know that. Uh, let's try to do a quick analysis of this equation. How to obtain this equation? So we know two things. One is force is equal to mass into acceleration. Okay. Also, we know that there is an equation, right? V square is equal to 2 into A into S. So where initial velocity is 0, right? Object starts from rest, it reaches to a velocity V. So V square minus U square is equal to 2AS was the equation. I'll make U 0, initial velocity equal to 0. Now, what is the work done? Work done is equal to the force into distance denoted by S. But from 1 and 2, I can rewrite force is equal to mass into acceleration. From the second equation, I'll try to write the S value. S is equal to V square by 2A. So you see AA cancels. So this is half mv square. So that's how we calculate this. Okay, with the mass and this. Now, the kinetic energy of uh, any object, right? We need to, whenever we try to calculate the kinetic energy by using this equation, we need to remember some of the important points, right? So that is, what is the value of m? M is the mass. Can it be negative? No, that is positive, right? So first thing to remember, m is always positive. Mass. Mass cannot be negative. There is no negative mass for of any body. There is no body with negative mass. That's why m is always positive. Fine. Second point is that, say, can velocity be negative? Yes, answer is negative. But v square is always positive, irrespective of whether you are right considering the positive velocity or negative velocity. V square is always positive. So since both m and v square are always positive, the kinetic energy of any system is always positive, and it does not depend upon in which direction the body is moving. So that's very important point to remember. Okay, so the note. So first point, since m and the v square are always positive, this implies the right kinetic energy is also always positive. This implies, right, the kinetic energy is independent. It does not depend on the direction of motion of the body, because as per our convention, right, something moves to the right is positive, left is negative, upward is positive, downwards is negative, etc. We have the convention, but that uh, convention, right, doesn't affect the calculation of the kinetic energy. So I'll write one simple notation here. The kinetic energy is independent, does not depend on the direction of motion. First point. All right, let's move further. The kinetic energy normally depends upon what is called as a frame of reference. Okay. Now that means the kinetic energy of a person is sitting in a train, right? So there, a person who is traveling in a train has a kinetic energy with respect to the earth, but no, his energy is zero with respect to the train, because train is also moving, he is also moving. With respect to train, the relative motion is zero, there is no movement. But with respect to earth, there is a movement. The person is moving with the velocity of the train. So right, you can consider mass of the person into velocity of the train square divided by 2 to calculate the kinetic energy of that person with respect to earth. Okay, but if you calculate with respect to the train, that will be zero, because no velocity, no relative velocity, both are moving at the same direction, same velocity, right? So that's the concept here. So this is the second point to remember, that is the kinetic energy depends upon the frame of reference. With respect to what frame you are calculating, it depends on that. Okay, later we'll solve problems of all the types. Let's move further. The next topic is called as the work energy theory. Right. Normally, this theorem tries to relate the work and the kinetic energy. All right. So let's try to give it a statement. The work done by all the forces acting upon a particle is equal to the change in its kinetic energy. So there are multiple forces acting on a body. Okay, and because of all the force, maybe the object moves by some distance. So right, so force into the the net effect of the force into the distance is nothing but the work done. Right, the same work done can also be measured by finding the change in the kinetic energy of that object. Initially, you may have some kinetic energy. After the all the forces act, the kinetic energy might get changed to a new value. Whatever is the difference, that is also going to give you the same answer equal to the work done by the forces. This is what is the meaning of this. So let's try to write an equation for this. So W net, the total work done is equal to delta, I'll write a delta notation, delta for small change or a change in the kinetic energy. So how do you calculate the change in kinetic energy? So this is the kinetic energy final value minus the, so minus the same kinetic energy of initial. Okay, so like that, we will be able to calculate. Now let us assume that there are multiple forces acting on a system, on a particular body or a particle. So let F1, F2, F3 dot 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 are the individual forces acting on the system. Let F1, comma F2 dot 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 be the individual forces acting on a particle. Right. Also, let the resultant force, let's call it as F, that is nothing but the vector addition, F1 plus F2 plus F dot dot dot, all are vectors. Okay, so we can find it like this. This implies, how do you calculate the work done? So therefore W is equal to integral of F force into the distance R dr, right? So I can try to rewrite this as, I'll use a bracket, F1 plus F2 dot dot dot, so many forces dot dr, the dot product. So we know that this integration, the whole concept of integration is based on the linearity in the sense, if you have, right, a integral being applied for a sum, integration of sum is equal to sum of integrals. That's what that means, integral f1 dot dr plus integral f2 dot dr plus integral f3 dot dr, and so like this we can calculate, right? So individual forces into the distances and integrate. Okay, so that's how we can try to calculate the total, what do you call, the work done whenever we have multiple forces in place. All right, let's go ahead, let's calculate, let's solve some problems. Okay, the question, an object gets displaced object gets displayed from 2 comma 3 comma 4 to 1 comma 2 comma 3, right, by a force denoted by F is equal to 2I plus 3J plus 4k, right? Calculate the work done. Okay, by using the conventional method, which we already have used in the previous classes, we get that the work done is equal to minus 9 joules. Now we'll apply a different method, right? That's using the concept we studied today. So we know that the work done, we use the following concept. Say dW is equal to the F dot dr. So normal method, calculate a dr from the destination minus the source into I cap, like plus j cap plus k cap, like that. We write an vector, take a dot product between the two vectors. That's the easiest way actually, right? So what we have done so far is the easiest one. But now since we have applied the concept we studied, we'll look at this particularly. Now, so this implies if you want to calculate the total work done, this is the integration of the dW, right? That is nothing but integration of F dot dr. But this F corresponds to, right? This integration should happen from initial to the last position. So we'll call this as the R initial to R final, right? The R value initial and RF for R final. So maybe this R is nothing but the initial position vector. So RF basically refers to the final one. Okay, so the final position vector. Right. So this is how we write the general dx, general representation for dr. Just remember is equal to change in x, that is dx multiplied by I cap. Change in y, that is dy, because y value is going to change when you move from one position to other position. The change in y axis is denoted by dy into the unit vector is j cap plus this is dz into k cap. This is what is a dr. Now let us try to write the equation. Therefore, w is equal to r initial to r final. I have to do the calculation later, right? This is the f dot dr. So r initial, look at the given values, right? They say initially it is located at 2, 3, 4. So this is nothing but 2. I'll just write 2 comma 3 comma 4 indicating that it's a starting position. Ending position is 1 comma 2 comma 3. Right, 2 comma 3 comma 4 to 1 comma 2 comma 3. Whatever is the f is nothing but 2 I cap plus 3 j cap plus 4 into k cap dot the dx into I cap plus dy into j cap plus dz into k cap. All right, so this is equal to, I still have to perform the integration. So integration 2 comma 3 comma 4 to 1 comma 2 comma 3, right? Now I know that dot product happens only between the, right, those components which have the same unit vectors. I into I, yes, I can multiply, right? That's why 2 into dx, 2 dx plus 3 dy plus 4 times dz. See the I, j, k vanished, right? I don't have to write that. Now I can actually do the integration. So integration is actually very simple here. The 2 is a constant. Dx integration is x. Only substitute the values of the function, values corresponding to the x-axis. X varies from 2 to 1 because I know that in the given coordinates 2 and 1 corresponds to the x-axis. That's why you write 2 and 1 over here. Then plus, next there is a 3, dy is y, substitute the values corresponding to y. Okay, so that is 3 to 2. So y changes from, y starts at 3 and goes to 2. So, right, you see, I just copied the same thing according to that. Right, followed by plus, this is 4, this is z, and I know that the z varies from 4 to 3. Why it is so? It is just because you can see 4 to 3, 4 to 3. So same things we copied according to the limits. Now simply substitute the limits because of the integration. This is 2 into, so upper limit minus lower limit. X, put 1 to x minus put 2 to x. So this is 1 minus 2 plus 3 times. This is 2 minus 3, right? Plus 4 times. This is 3 minus 4. Every difference is 1. So this is minus 2, minus 3, minus 4. So you have the answer that is equal to minus 9 joules. Okay, right. So this technique is actually the mathematics related to the concept which we have studied. Okay, so this is important. Actually, for this particular solution, we don't have to go to this method, but for many other methods, we require these kind of calculations. So understanding this concept is also very important for that. So, but let's solve another problem using this method, the new method. Okay, so position vector I'll write R1 is equal to 2i cap plus 3j cap. Okay, that is R1. The position vector of the second location is 4i cap plus 6j cap, and the force is 3x square into I cap plus 2y times j cap newtons. So object moves from R1 to R2 under the force given by this equation. Now the question is, find the total work done by this force. Okay, so the normal equation under this concept is integration starting from R1 going till R2, the force, that is F dot dr. So we know that dr is a fixed quantity here. So let's substitute the values. This R1 means this is 2 and 3. I can see that 2 and 3. Right. That's why the x value is starting at 2 going till y value starting is 3. So the destination shows 4 and 6 means x value is 4, this is 6. Right? Okay. Let's write the force. Force is 3x square into I cap plus 2y into j cap dot, I have to write the dr. What is dr? Is dx into I cap plus dy into j cap plus dz into k cap. So dr is always this. I don't have to change this. Okay. This is equal to, so once again, this is 2 comma 3 to 4 comma 6 multiply. So 3x square dx plus 2y dy. There is no z. Dz does not get multiplied to I and j because product is 0. So only this much. Right? So this means, now let us separate. So let's do the integration. So 3 is a constant. X square dx integration is x cube divided by 3. And I should substitute 2 to 4. Plus 2 is a constant. Y integration is y square by 2. So limits 3 to 6. So anyway, this cancels, this cancels. So this is equal to 4 cube minus 2 cube plus 6 square minus 3 square, because this 6 goes to the y, 3 also goes to the y. That's why 6 square minus 3 square. For the first integration, for the first term of this integration, 4 goes to the x cube, then 2 goes to the x cube. That's why 4 cube minus 2 cube. Right. So let us simplify this now. Okay, this comes to be 83 joules. Next question. The starting position is -3, comma 2, comma -4. The destination is equal to 3, comma 4, comma 6. The force is 4x into I cap minus y square by 5 into j cap plus z cube divided by 8 into k cap. So we have to use the following. Integration of x dx, right, becomes x square by 2. So if you have integration of y square dy, that becomes y cube by 3. And if you have integration of z cube dz, that is z to the power 4 divided by 4. Use this. Use. So the work done is 400 joules.